All right, we're going on a bug hunt today. And our target? Well, it's one of those mysterious, sneaky culprits that every single iOS developer runs into eventually. We're talking about the race condition. Let's crack this case. You know exactly what I'm talking about, right? Your app crashes, but it's totally random. It only happens for some users some of the time. So you go to replicate it, you fire up the debugger, you sprinkle in some print statements, and poof, the bug vanishes. It's like a ghost in the machine. It is one of the most frustrating things you can deal with as a developer, but today we're going to unmask this thing. So, this phantom bug of ours, it has a name, a race condition. And it's exactly what it sounds like. You've got two or more parts of your code that are literally in a race to get to the same piece of data and change it. The problem is, the winner of that race determines the final outcome. And since you can never, ever predict the winner, your results become completely unreliable. To really wrap our heads around this, we need to get our hands dirty. Let's investigate a crime scene. We're going to look at a super simple piece of code where a race condition is hiding in plain sight. Okay, here's our setup. We've got one shared resource, this variable called count. Now, just imagine this is something important, like the number of items in a shopping cart or the like count on a photo. Then, we kick off two different background threads, and we give each of them the exact same simple job. Add one to count. Seems easy enough, right? The final result is obviously going to be 2. Or is it? So here is where it gets wild. The actual result is totally unpredictable. Yeah, it could be 2, but a lot of the time it's actually 1. So what is going on? Well, think about it. Both threads might read the value of count when it's still 0. So thread A reads 0. Then, at almost the exact same microsecond, thread B also reads 0. Now, thread A adds 1 to the 0 it read, and it saves the result. Count is now 1. But a split second later, thread B, which is still holding on to that original 0, it adds 1 and also saves the result as 1. We just lost an entire operation. And that right there is the heart of a race condition. So, we've seen the crime. Now, let's build a profile of our culprit. If we know what to look for, we know how to catch it. Understanding its MO is everything. First thing, this bug only shows up in concurrent environments. That's just anywhere your code is trying to do more than one thing at once. Second, it always involves a shared resource, a variable, a file, an array that multiple threads are trying to mess with. And finally, because its very existence depends on split-second timing, it is incredibly hard to reproduce on demand, which, as you know, makes it an absolute nightmare to debug. And make no mistake, the damage this bug can do is serious. We're not just talking about a number being off by 1. This can lead to completely mangled data, users seeing totally wrong information, and in the worst-case scenarios, those weird, unpredictable app crashes that tank your App Store reviews and drive you crazy. All right, enough about the problem. Let's talk about solutions. How do we, as the bug detectives, catch this thing and stop the crime from ever happening? It's time to open up our toolkit. You know, the classic tools are all about one thing, enforcing order. A serial queue, for example, is like making everyone get into a single file line. Only one operation can happen at a time, period. A lock is kind of like putting a key on a room. A thread has to grab the key, go in, do its work on the shared data, and then put the key back for the next thread to use. Both of these methods achieve the same goal. They stop two threads from acting at the same time. So ultimately, it doesn't matter which tool you reach for. The goal is always, always the same, ensuring controlled, predictable access to that shared data. You're basically stopping the race before the starting gun even fires by forcing all the threads to take turns nicely. Now, those classic tools, they work, for sure, but they can be a little clunky to manage. Thankfully, modern Swift has handed us this incredibly elegant and powerful weapon that handles most of the hard work for us, and it's built right into the language. Everybody, say hello to the actor. An actor is a special type in Swift, and it was designed for one specific purpose, to solve this exact problem. You can think of it like a little vault for your data. It automatically manages everyone trying to get in and out, making sure only one thread can access the data inside at any single moment. And this is the best part. Look how simple it is. Instead of just declaring a variable, we wrap our value inside an actor that we're calling counter. That's literally it. Just by making this one little change, the Swift compiler now enforces safe access for us. If you want to read or change that value from outside the actor, you just use the await keyword. That tells your code, hey, pause here and wait for your turn. It prevents the race condition automatically, behind the scenes. It's thread safety made simple. So, how do you choose which tool to use? Well, serial queues are still great for simple, ordered background jobs. Locks are still really useful, especially if you're working in an older codebase or dealing with some legacy APIs. But honestly, for any new code you're writing in modern Swift, actors are almost always the right answer. They're safer, they're way cleaner, and they let the compiler be your partner in preventing these bugs from ever happening. So, after this whole investigation, here's the final verdict. The one thing to remember. Race conditions happen when timing affects correctness. Our job, as developers, is to get that unpredictable timing out of the equation. And that brings it all back to you. Now that you know how to spot a race condition and how to fix it, I want you to think about your own apps. Where do you have data that might get accessed from multiple places at once? What counters or user profiles or shared data arrays need a bodycard? It's time to be the detective in your own code. Thanks for tuning in.